嗯哼，
我现在就106个人。
Hello, good morning. 哎，开始。嗯，
你有点哦。
有啊。
哎呦，开始。
Hello. 哎，good morning. Good morning. Let me see. I'm checking also the chat room. Okay. Hey, hi. Hi. Okay, so we'll wait for a while before we start. Okay, hi. Oh, hi, Brian. Good morning, good morning. Hello. Hello, hello. Okay, so we'll soon start in 1 minute. Okay, so my clock says it is 11:10, so let's start the class. So So welcome to this course. So today we are going to make a very quick summary of the topics that we are discussing this week. And then, so let's first start with the overview. So first of all, you can all download the notes from my webpage, and then so you see that I've written content.html here. Actually, this is so I've been teaching this course for many years already. So the class notes are actually similar or exactly the same. So you can download whichever version that you like. And then if you have any problems that you want to ask, you can find me easily at my email account. And then we have TAs here. So this year we have 5 TAs. And then the information can be found from the EE class system. So the running for this course this year is going to be online. So I hope, okay, maybe if there is some chance, then we will see if we can meet together. But then basically, so we will be running this online so that all the assignments are submitted online and even the exams are done and individually at home, and then so that you can submit the solutions online. And then for the Thursday class, every week we will assume that you have already watched the OCW recording for that week. And so on Thursday, we will talk about a quick summary for that. And then every Tuesday, we will spend 1 hour as a tutorial and looking at some examples of the topics covered in the previous week. And then we will also answer students' questions. So we will collect your questions online until Saturday. So we will collect the questions and then try to answer them during the tutorial. Okay, so this course is about an extension of the discrete maths. So you will see a lot of familiar things that you have studied before. For instance, we will talk about permutations and combinations, the counting problem again. And hopefully, I hope that we can see a little bit more interesting examples than you have seen already in the undergraduate class. We will also talk about generating functions. So for this one, I know that this is taught in some undergraduate class, but then for my class, I didn't do so. So I will be talking about generating functions again here. And then we will also talk about another related topic called recurrence relations. And then after that, we will talk about some skills for doing the proving. So they are the topics that, so actually I've taught most of them during my undergraduate class, but then we will see some other new examples there. So we will talk about induction, we will talk about proof by contradiction, some pigeonhole example, pigeonhole principle example. And then we will look at some very basic number theory. So hopefully this will give you some idea of the interesting part of this. And then if you want to study more, then you can later take the number theory course from the math department to learn more. And then we will also talk about group theory. So this is algebra. And then if we have time, we will talk about automata theory. So automata theory is also something that we will study in the formal language class or the introduction to theory of computation. So that's it. Okay. Now these topics, although they are purely discrete math, but they can be used in, for instance, the group design, the group theory can be used in code design. The number theory can be used in cryptography. Automata is related to theory of computation. And then then we have counting or things related to data compression. And then methods of proving is related to the analysis of algorithms. And then counting also again is related to network design. And then for so the materials from this book I have selected some of them from the corresponding 3 books. So the first one is Introduction. Excuse me. So I forget to turn on my phone. Excuse me. Sorry. 喂，对不起，我现在上课。好，好吧。Okay. Sorry. Ah. Oh, okay. Accident. Okay. So the first one is Introduction to Combinatorial Mathematics. It is a book written by our former headmaster, Professor David Liu Chonglang, CL Liu. So it is a very old book, but then full of excellent examples. So I have selected some of them, some of the topics there, and then to put it here. And then another book is called Concrete Mathematics. So it is written by 3 guys. One of them is Ronald Graham, and then the other is the famous Donald Knuth in computer science, and then the last one is Patashnik. So this book is fun. Okay, so I've collected some of the fun topics there and then put it in here. And then the third one is called Proofs from the Book. Okay, so it is written by these 2 guys, Eichner and Siegler. So this book is written in honor of the mathematician Paul Addis. So Paul Addis is a very famous mathematician who works around the world with many people. So he has published perhaps, I think this is still a record, the most number of papers, mathematical papers so far. Okay, but if you talk about the content wise, so the total number of pages, okay, in publication, so there is another one who may be having more publications. So the other one is Euler. So Euler from the Switzerland, long time ago. Okay, so 1700, around that period. So Addis has a theory. So he says that okay, all the mathematical theorems, there will be a proof, but there is only one proof, which is the simplest, the best. Okay, and then this best proof, the simplest one, the easiest one to understand, this best proof is collected in God's hand. So only God has the proof for every theorem in the best way. And then the task for a mathematician is to discover such kind of proofs. So in this book, we will see a lot of different famous theorems, and then they have, so like what? Like the Pythagoras theorem, or there's a theorem called prime number theorem. And then, so there are lots of different famous mathematical theorems, and then it has collected a lot of simple, easy to understand proofs. Very brilliant one. So if I have a chance, then I would like to show you some of them during the tutorials. Okay, so for our assessment schemes, so we will have roughly 5 to 7 assignments, and then most probably 5. But then if we have more, then it's like this. So for the 5 best assignment, you will get 50% of the mark, and then the remaining 2 you will have 5%. But if there is 5 assignment, then we will adjust this. Perhaps like the best 4 will contribute 50%, and the remaining one will contribute 5%. So don't worry. So we will not take you 5% from the beginning. Okay, so the assignments will cover 55% of the totals, and then we have altogether 3 exams. Each one of them carries equal marks, so 45% in total. In that case, 100%. And then, so we will be having the exams unless there is some accident. Okay, so we will be holding the exams on week 8, week 13, and also week 18 of this semester. So if you have some problems about attending the exams, just let us know so we can arrange a makeup exam for you. So don't worry if you are really not able to attend the exam that week. Okay, so This is the study tips. Okay, so always try to have a fresh mind in class and then ask us questions. Although it is unlike the face-to-face course that we cannot answer you questions face-to-face immediately. Yeah, please do ask us questions. So you can send us questions by the chat room bulletin board, or you can send us question before Saturday each week so that we can collect them and then answer. And then try your best to do every assignments, and then we really encourage you to work in groups so you can chat, you can talk, you can discuss with your friends, with your classmates. But then make sure that in the end you need to write down the answers independently. So not like you do one thing together and then copy the others. It's not good. So you can what is the best way? The best way is to do discussion with the classmates up to a certain level, high level discussion maybe, so that everyone will have freedom to complete the details of a certain assignment question, and then you write down in your own way. Okay. And then the other is discuss with others, help the others. So helping the others is the best way to learn, because by making sure that you can teach the others correctly, that means that you have already be sure that you are understanding everything fully. Okay. And then finally, this course, like the discrete math class, so it will be full of interesting puzzles. So I hope that you want I hope you will like it, and then try to have fun. Okay. So this is it. So this is an overview. So let's do the lecture. Okay. So we are really doing a very quick summary. So if you want to know more about the details or a slower version, please do and check the OCW recording. Okay, so the first topic that we are going to cover is permutations and combinations. So today we will look at some of the notation, and then these two basic rules. They are very, very easy, but then powerful to derive all the counting problems and theorems we have in this class. And then we will look at a little bit on permutations. Okay, so notation. Okay, so in counting problems, we are interested in these particular two types of problem. One is the selection problem, and then the arrangement problem for the other. Okay, so first of all, selection and arrangement of objects appear in many places. But for this one, so of course, sometimes we will want to list out all the different. So let's say we have 5 objects, A, B, C, D, E, and then we want to ask how many ways can we select 3 objects from them. Sometimes we want to list out all the possible ways that we can select 3 objects, but sometimes we just need to find out how many ways are there, the number of ways are there. Okay, so let's say this one. This is the first example. So how many ways can we select 2 people from 5 candidates? So this is not difficult for us because the numbers are very small. So by doing a lot of listing, so we will, let's say the people are A, B, C, D, E, and then to get 2 people. So here selection means that we don't care about the ordering. So we may be selecting A, B, or A, C, A, D, A, E, and then what? And then B, C, B, D, B, E, and then C, D, C, E, and then D, E, something like this. So altogether, after doing some brute force checking, we will find that there are 10 different ways of doing so. And then here, so the next question is, how many ways are there to arrange 5 books on the bookshelf? So if you have seen this problem before, then you can quickly count that. Oh, the number of ways is 120. 120 corresponds to 5 times 4 times 3 times 2 times 1. Okay, now in most of the textbook that we use, the word combination and selection, they are interchangeable. So how many ways to select things is asking how many combinations are there. So here, this is the first word. Okay, so we want to say what is an R combination of n objects. Okay, so here it means that, so altogether we will consider n objects, and then we look at the combination. But then there is a description, R combination. R combination means that for each combination that we look at, we want to have exactly R objects. So this R is an adjective to describe the combination that we like. So an R combination is simply an unordered selection of R of the objects. Okay. So for instance, suppose the object is A, B, C, D, E, and then we want to get a two combination. So what is a two combination? So any selection of two objects is a two combination. So CD is a two combination. Okay. And similarly, we have the word permutation, which corresponds to arrangement. And then we have R permutation of n objects, means that it is an ordered arrangement of R objects of the objects. So for instance, suppose that we have A, B, C, D, E, then a 5 permutation will be a permutation consisting of selection of 5 objects here and then do the arrangement. So CBADE is a 5 permutation of the objects. So here, the permutation here, we require that there is no repetition of the objects. So they are formed by distinct objects. Okay, now, so we are focusing actually not listing out all the combination, not listing out all the permutation, but we are interested in doing the counting. So we want to count the number of different R combinations that we have, and also the number of different R permutations that we have. So we will use this notation CNR to denote such a number of combination. Okay, CNR, C means that we are interested in counting the combinations, and then altogether there are n objects that we can be using, and then each time we can select R objects. So CNR is the number of ways to select R objects out of n. And similarly, PNR is talking about permutations. We want to count the number of permutations, and then where we want to count the number of permutations that we have a total of n objects that we can use, and then how many of them will have exactly R objects using. Okay, so let's take a look of these to check our understanding quickly. What is the value of CNN? Okay, CNN is the number of ways to select n objects out of n objects. So unless we are talking about the special case C00, but let's say C55. So I have 5 objects. How many ways can I select 5 objects? So there must be one way. So because I need to take them all. There is no other way. So CNN is equal to 1. And how about CN1? CN1 here is that I have n objects that we can use, and then how many ways I can select exactly one object. So the answer will be n normally, okay? So unless n is equal to 0. So let's forget about this extreme case. So CN1 is equal to n in general. And then what is C32? C32 is I have 3 objects altogether. How many ways I can select 2 objects? So let's say the 3 objects is, so that we look at our A, B, C. So there are 3 ways that we can do the selection. One is AB, one is BC, and then the other is AC, something like this. We don't remember here when we do the combination, we don't care about the ordering. So there are 3 ways here. And then P32 is I want to find out permutation this time, arrangement. So I have 3 objects that I can choose, but then each time I must be using exactly 2 of them. So let's say again we have ABC. So the number of arrangement that I can form is AB, BA, AC, CA, BC, CB, something like this. So by brute force listing, then we can find out that P32 should be equal to 6. Now at this moment, all these values, we are arguing why they are such, okay, by using logic, okay. So we don't have any formula for doing so yet. We will talk about the formulas for them later, but then we are not actually relying on the formulas to solve them. Okay, another example. Okay. So we will talk about them later, the formulas. Okay, now the next one that we want to talk about is rules of thumb and product. So there are 2 rules. One is called rule of thumb. The other is called rule of product. Okay, so they are simple things, super simple. Okay, so let's see this example first. Now suppose that we have Roman letters A, B, C, D, E, and then Greek letters alpha, beta, and gamma. So how many ways to select two letters? One from each group. And then the other one is how many ways to select one letter that is either a Roman or a Greek letter. Okay. So in the first one, how many ways to select two letters, one from each group? So we know that there are 5 ways to select a Roman letter. And then after the selection of a Roman letter, and then for each of them, there will be 3 different ways to select the corresponding Greek letters. So in the first example, we will see that there are 15 ways, like A alpha, A beta, A gamma. So this is by selecting A first, and then select the Greek letter. So A alpha is one way, A beta one way, A gamma one way. So 3 ways, B alpha, B beta, B gamma 3 ways, and so on and so forth. So altogether, there are 15 ways. And then this 15 corresponds to 5 times 3. Okay. So this is 5 times 3. So this is the answer for the first problem. And then, but the other one is, how many ways to select one letter that is either a Roman or a Greek? So we don't care what kind of letters that we select. Any letter that we select will be okay. But how many ways to select one letter? So there are 5 ways to select Roman, 3 ways to select Greek. So altogether, there are 5 plus 3, 8 ways to select one letter from either of them. Okay. So this is going to be, the answer is going to be 8, but then 8 comes from 5 plus 3. So we will see that, oh, one of them is like doing the multiplication, and then the other is doing the addition. So in general, this is what we observe. So if, let's say, one event can occur in m ways, for instance, like selection of a Roman character, and then another event can occur in n ways. So another event, let's say, selection of the Greek letters. So there are 5 ways here, and then 3 ways here. Now, rule of product says there are exactly m times n ways that these two events can occur together. So this is like the first one occur and the second occur. This is like the AND operation. On the other hand, rule of thumb says there are m plus n ways that one of these events can occur. So not together, one of them. So either this or that. So this is or. So if we are doing AND, the logic AND, one thing and the other, then it is applying rule of product. And then if we are doing one thing or the other, then it is using rule of thumb to do the counting. Oh, double check our understanding. Okay. Okay, so we have this question. Suppose that there are 5 Chinese books, 7 English books, and then 10 French ones. So how many ways to choose 2 books of different language? So here, so if you are so familiar with all these, formulas for the CNN or CNR or PNR, something like this, then maybe you will fall into the trap of answering this question, because there is no single formula that can answer this immediately. But on the other hand, we can use rule of thumb and rule of product together to help us. Okay. So first of all, the selection of 2 books of different languages, we can look at them we can classify these ways into 3 types. One is the 2 books are, because we need different language. Okay, so maybe we are selecting 2 books such that one is Chinese, the other is English. So Chinese with English is one way. Or we may be selecting a Chinese book with a French one. So Chinese with French is another way. Or we may be selecting an English book and a French book as another way. So English and French. So there are 3 different types of language selection. Maybe Chinese with English, Chinese with French, or English with French. So there are 3 different types. And then for each type, then let's say for Chinese with English, we can easily count them as there are 5 ways in Chinese, 7 ways in English, but because we need to choose a Chinese and an English one, so it is AND. So there are 35 ways here, 5 times 7 for the case Chinese with English. 5 times 10 ways for Chinese with French, and then 7 times 10 ways for English with French. Is that okay? Now, because this way or this way or this way happens, and then these are all talking about different ways. Okay, so we are going to add them up together. So altogether, this gives us the answer. So we can solve this problem by using rule of thumb and rule of product together. Okay, of course, this is not the only way to solve this problem. We can also use rule of difference, okay, the subtraction, to solve it. So we can consider the other way of solving this, but then I will leave this for you as an exercise. So the other way is, let's consider all the different ways of choosing two distinct books. So all different ways. Okay, so I don't care whether they are Chinese with Chinese or Chinese with English or whatever. So any way of choosing two books. So this is total number of ways that we have. But then we have overcounted. So some of the ways we don't want to be counted. So we don't want to be counting the number of ways of selecting Chinese with Chinese. We don't want to find out the ways for, we don't want to count those ways for selecting English with English. And then we don't want the cases with for the French with French. So we should subtract those cases that we don't want. So we can also do this by calculating each of these cases correctly, then we should get the same answer. So for you, perhaps you can use your own, so I believe most of you has known the formula for CNR. So you can try to get a different way of proving the same thing. So I want to emphasize one thing in this class, okay? This is the math class. So we are going to do a lot of calculations, provings. So for most of them, there is no unique answer. So as long as your answer, as long as your proof are correct, we will be giving you perfect marks. So there is no single proof that we want, okay? So it would be great if you can provide us with different kinds of ways, smart ways, so that we, like me and also the tutors, can also learn from you, okay? Okay, now, so we have a bunch of formulas that we can see here. Now, here, we want to ask you, why are the following formulas are correct? Now, we don't know what is the value of PNR yet. We don't know the formula of PNR. So later we will see that, but now we don't. But then still, I want to argue that for any case of N and R, PNR is always equal to PRR times CNR. So why is it true? So this is done by rule of product. So what is PNR? PNR means that I want to find out the number of ways that we can pick items, n of them that we can choose, such that each of the way corresponds to an arrangement of R of these items. Okay, the number of ways of doing so must be equal to the number of ways of doing what? So because I want to have R items in total, right? So each of these way corresponds to what? First of all, I try to select which R items that I want. And after the selection of the R items that I want, I am going to arrange them because each of the arrangement will correspond a different way. So to get an R arrangement, to get an R permutation, what we are going to do is we first select R items and then arrange the selected R items. The number of ways to, so this is like doing two events at the same time together. First, we select R items. So there are n choose R ways, CNR ways of doing so. After that, we have R items left. And then we want to make any arrangement of it. So there are how many ways? PRR ways. So in that case, this is a perfect example for using the rule of product. Okay. And now, why is it true that PNN is equal to PNR multiplied with PN minus R and minus R? So PNN means that I have n items. I want to get the full arrangement of these n items. Okay, PNN. So to get such a full arrangement, then what we can do here is that, okay, so let's say we are lazy. Here we are going to do the arrangement of n items in one batch at the same time. So we are doing this. But then let's say we are lazy. So what we can do here is that, okay, so let us pick out R items first and do the arrangement. These are the first R items that we are going to see at the beginning. And then after that, so after doing this selection of R items and arrange them, then the next part is we have remaining items. So we are arranging them now. Okay, so we first arrange R of these items, and then we arrange the remaining items. Altogether, we will get the full arrangement of all the n items. So this is again, we will see that the number of ways of doing so, Pnn, must be equal to the number of ways of selecting R items and do the arrangement. And then after that, we have n minus R items left, and then we do the arrangement of the remaining n minus R items. So Pn minus R, n minus R. So using this argument, we will see that this is always correct. And then the third formula here is CNR. Oh, don't worry if you think the pace here is very fast. Okay, so what I recommend you is really to check the OCW recording before coming to this class, and then here it is just like a very quick checking of what you have studied and whether you want to ask me questions here immediately. Okay. So the third one is CNR. CNR is the number of ways of choosing R items. And then we are saying that this is equal to this term plus this term. Okay, this formula has a name. This formula is in European countries, okay, or so this formula is called the Pascal formula. So this is somehow discovered by the French mathematician Pascal. But actually, in ancient, not that ancient, okay, in I think the Song dynasty in China, so the mathematician Yang Hui has already known about this formula. So this is the same formula that is discovered at different time in history, but then it is now more popularly known as Pascal formula because English is the dominant language in the whole world at this moment. Okay, so let's get back to the formula. So it says that CNR is equal to this one and plus this one. So CNR can also be read as n choose R. So n choose R is equal to this one. So to select R items out of n, so we can view it as this following case. So let's say we mark one of the n items here as special, and the other are the others. Okay. Now, when we select R items, there are two different cases. One is we are selecting this special item. The other case is we are not selecting these special items. So we will count the number of ways of choosing R items, but then we must select the special item. And then we also count the number of ways of getting R items, but then we cannot select the special item. So these two number of ways should add up to CNR. Okay, the number of ways that we must include the selected, we must include this special item is what? It is equal to Cn minus 1 R minus 1. It is because of what? Because the special items is already selected. So the number of ways must be equal to, we need to find out which R minus 1 items that we need to select out of the remaining N minus 1 items. So this is the number of ways of including the special item. And then how about the other case? Suppose that we must not use the special item. So in that case, the R items must be coming from the remaining N minus 1 items. So the number of ways of doing so, by definition, is C N minus 1 R. So N minus 1 choose R. So this is correct. Now, this is important, okay? The way that we are proving these things are correct, they are just based on the definition, the meaning of each term. So we use what is the meaning of this term and what is the meaning of this term, and then we argue that they are correct by using some understanding, like rule of thumb, rule of product, this basic logical arguments. So we are not using any mathematical computations or a lot of different formulas. We don't know PNR. What is PNR? What is? We don't know. We just know the meaning of PNR. Now, so this type of arguments that doesn't require or requires only very few calculations, we call them combinatorial argument. So we are basing on the combinatorial nature of the terms here, and then argue that this combinatorial term follows certain properties. So we call this combinatorial argument, or sometimes we also call it double counting. We are counting the number of ways of doing one thing in two different methods by using two different methods. So this is like selecting our items in one batch. Okay, but here this is like we are selecting items based on whether we have the special item or not. So this is one way of counting. This is one way of counting. They are counting the same thing, but then in different ways. So because they are counting the same thing, so they must have equal value. So in that case, this is called the double counting technique or the combinatorial argument technique. So in many exercises or the exam questions, we will ask you to prove something like this. A certain formula is correct by using combinatorial argument. So we will expect you to answer this in this way. So if you are using the formula of PNR to do so, then we will normally mark you as zero marks for that because we will see that you are not understanding what is the meaning of combinatorial argument. So why we think that this is important? Because combinatorial arguments sometimes can make the proof very easy. Okay, so you will see. Okay, so you'll be happy that in your assignment question you will see a question that you can answer it in combinatorial argument rather than the other way. Okay, so let me see. So we are going to end up with this last one. So this is the last part for today's lecture. So here, this is the first time that we can give the formula for PNR. Okay, so here, this is like PNR. We want to argue that PNR is equal to n times n minus 1 times n minus 2. So they are here all together. You start from n. There are r terms together. So 1, 2, 3 up to r terms. So this is rather easy. So you don't need to calculate what is the last one. So it is n times this one times this one. So this is the formula. And then I think you are all familiar with the notation n exclamation mark. So this is n factorial. N factorial means n times n minus 1 times n minus 2 up to 1. So you can see that this value is equal to n factorial. You start from n up to 1, but then you don't want to have the remaining part. So you divide this by n minus r factorial. So this is n factorial divided by n minus r factorial. So how do we prove this? So we can prove this by combinatorial arguments. So the number of ways to get R objects in certain order, in some order, okay, so we want to arrange them. So there are n ways to select the first one, and then n minus 1 ways to select the next one, and so on and so forth. So we get this formula. So that's it. Okay, or you can also use this PNN. So PNN is the number of ways of arranging n objects. So how many ways are there? So n ways to get the first one, and then for each case n minus 1 way, and then and so on and so forth. So PNN is n factorial. Now if PNN is n factorial, then Pn minus r n minus r will be n minus r factorial, and then PNR will be n factorial divided by n minus r factorial. Okay, and finally there is a very handy notation that I want to introduce. So if you check the OCW recording, so I will have a notation. It's like n to the power r, but then there is a bar below r. So check the OC. Let me see if I can type. Yeah, not easy to type. So next time maybe in the tutorial I will write it down for you. So it is like n. Okay, imagine I'm drawing an n here. N to the power r. But then after the r there is a little bar here. Yeah. So if you look at this term, it is if n is super large, this is like n, this is like n, this is like n, this is like n. So it is roughly like n to the power r. But it is not exactly that. It is because for each of them, the next one is one smaller than the previous one. So n times one smaller than n times one smaller than n minus 1, and so on and so forth. So we will call this n to the power, this is the falling power of n to the power r, but then with a bar there. So in that case, then yeah, I hope that this notation is very, so what it needs here, it is rather than you memorize things like starting from n and then ending up to n minus r plus 1, what I hope you to memorize this is like you start from n, but then there are r terms. Each term is one less than the before. So starting from n, there are r terms. This is the natural meaning of this equation. Okay, so that's all that I want to show. So for the next class, so we will still have a class on Tuesday. So I know that this is a holiday, so you are, yeah, but the YouTube live here will be recorded. So if you can join, then join. If you cannot, then you can look at it later. So the next Tuesday class will be about some examples. Or of this one. So I will try, and then basically to answer the questions that we have collected during the weekend. Okay, so that's all. Okay, and then yeah, I have seen that there are some message here in the discussion group. Yeah, so some students said it recommend the book How to Solve It by Polya. Yeah, this is an excellent book. Okay, if you read the but then really try to get a, I don't know the Chinese translation, but then the one, but then the original one, the book, the layout is not that friendly. Okay, but then it is a super good book. So How to Solve It by Polya. And then another one is Richard Stanley's Algebraic Combinatorics and Enumerative Combinatorics. So Richard Stanley is a super famous mathematician. Yeah, I think from, let me see, I forget, MIT or Harvard, one of them. Yeah, one of them. Let's say MIT, perhaps. Yeah. So yeah. So if you are interested in combinatorics, yeah, look at them. But algebraic combinatorics, maybe it is like a more advanced one. But then if you like it, then yeah, check out these two books. Yeah. Thanks a lot for the message. And then yeah, I think that's all for today. And then yeah, see you next time on Tuesday. Yeah. Thank you. Okay. So thanks all.